Okay, so this is ratchets and pawls. Alright, so a ratchet is a device that allows motion in one direction but prevents it or positively prevents it in another direction. Alright, so I'll just give you an example here online. Alright, so these are just some examples when you do a Google search. Right, and we could see here that we have this motion that could be rotation counterclockwise, but if we were to try to reverse the direction, it would engage what we call the pole. So therefore, the torque or what it is we are trying to prevent, or the motion we are trying to prevent, the pole would therefore have to take that load. Right, there are other configurations here. Here we have a spring that that ensures that the pole is always engaged. So you need a force to release the pole. Right, and it is a safety mechanism. Right, we could have this in a linear sense that will allow motion up but prevent motion down unless it disengages the pole. Or you could have it as a driving mechanism. So this is what you would see in a one of those tie-down straps um, that were used on vehicles and trucks and stuff, where you have the arm when it moves back and forth, you can actually drive the ratchet wheel forward, right? And then when you retract, it would allow the pole to go over and then grab again from a lower point and then drive it again forward. Right? So when you release the driving pole, the locking pole will engage and prevent it from going backwards. Right? So that is essentially the operation of a ratchet and pawl mechanism. Right? So what we have here is an internal ratchet and pawl system. So instead of it external, which is like the photos we just now saw, here we have the pole on the inside. And the calculation is the same. Right? So I will just highlight some of the forces here. Right? So if we have rotation in this direction, then therefore we're going to have a force P in that direction. Right? If you were to zoom in here, we're going to see that is the tooth of the ratchet, and then you have the pole going forward like this. Right? So we are preventing motion of the ratchet. Right? So in order to do that, that force P is being applied here. Right? And then also, if we have a normal force and we have metal on metal contact, or we have two surfaces on contact, we're going to have some frictional force. Right? So ideally, we want the pole to rotate inwards like this. That's to ensure that, in terms of a safety perspective, we want to ensure that the pole is always engaged. So the greater this torque is, we want the pole to be engaged more and more. We don't want it slipping out, and whatever safety mechanism that will be preventing from falling, we don't want that to happen. Right? So we want the pole again to be rotated in this direction. So that means a frictional force will be opposing that, which will be in this direction. Right? And that frictional force will be coefficient of friction by P. Right? Now, if we were to just look at some dimensions here, I'm just drawing it over because it's just probably not clear enough. And we have some distances here. Right, if we take moments about the center here, the rotation of the pole, because remember we're saying that the pole, this is the pole, and this entire thing is rotating up like this. Then we could say that in order for the pole not to slip out, we could say that P by C, right? So that's this force here, P times C, which is the engaging moment, plus the weight of the pole, because we say the weight of the pole is acting down, right? And we say the weight, that moment is just M, right? So this is the moment due to weight of the pole, right? That moment, this total moment must be greater than the friction times B, right? The moment due to the friction plus some friction within the shaft of the pole then, right? So that term here, right? I'll just have to need some space here to explain that, right? So if we have This is the forces on the pawl right now, right? I could actually draw it here. Right, so we're gonna have a force in this direction here. That is the resultant of P and mu P. So of course this force would be what? P squared plus mu, right? That's the reaction. Right, so this is really P into 1 plus mu squared. Right, so that is the force. Right, so we have now on this circle here, we have, this is how the, right, or we could just draw that force on the side here. Right, and then we have a small radius here, R1, as the radius of the shaft, that's pink shaft. Right, that's this here, that's that shaft. Right, and then we also have a coefficient of friction, because remember that is sliding about a bush, or something. Right, so that will generate, this friction will generate a frictional torque then, and that frictional torque would be this force times mu, right? So the frictional force will be, right? And now the torque due to that frictional force will be that whole thing multiplied by R1. So this is frictional force times, we forgot the mu1 here. Right, that's the coefficient of friction between the pawl and the shaft or whatever. So that entire frictional torque will be times R1. Right, so let's make this a little clearer for you all to see. Right, so that is the, again, the opposing torque. Right, so that is what we have here now. They made a mistake in these notes here. So this is the actual term here. Right, so this here is the equation that governs the pawl not escaping. Right, and in order for the pawl to remain engaged, the moment that is pushing the pawl into the ratchet must be greater than the moment that is trying to release it from the ratchet. Right, so if we ignore the things like the weight and we ignore that pivot friction, right, because I mean we could just lubricate and to make mu1 very small so that we eliminate that torque, then we end up with this simple equation. Right, so the rest is just algebra, and what it works out to be is that if it is we using a coefficient of friction of 0.15, then we say the ratio of small r to big R must be between this range. Right, small r being the radius, the internal radius of the ratchet, and big R being the external radius of the ratchet. Right, so you could go through the derivation here. And that is to ensure that in the design of a ratchet and pawl, that when the pawl is being engaged, if the torque were to increase, it wouldn't just spring out and the pawl would slide out and cause some kind of catastrophe. Right? Another type of pawl here is one that hooks on the outside, and this is common in driving systems. By driving systems, I mean you have some lever attached here, and when you pull the lever, it will pull the pawl. Alright, so that's it in terms of the technical side of ratchets and pawls. This here is an example of a data sheet when you're looking to buy an actual ratchet and pawl for an application. And I would give you some equations here as to how to go about calculating the torque capabilities. Here, you notice it talk about bending strength, right? And bending strength, of course, has to do with the strength of the bending strength of the ratchet itself. Sorry, of the pawl itself. Because if you notice, it's like a beam, right? Alright, this is just again an example of application. Here we have the spring. Alright, these two applications here. What we have here is a motor that is rotating this rack up. So it's like the rack on your gate, but it's imagine in a vertical sense. So it could be a lift for a car, for example. Right? And in fact, when you're doing any maintenance in the car and the car is being lifted, you would hear clunk, 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 clunk. That clunking noise is the ratchet and the pole. Right? Now, this lifting device, when the load is being applied, the ratchet will keep everything in place. When time to lower the load, this pole now would have to be lifted, and then the lifting device will be able to come down. Another example application here is in worm wheels or worm gears. Right, on a worm gear, typically we have one directional rotation. Right, but if the force is applied high enough to this gear, we could actually drive the worm wheel, which is undesirable. Right, so again, we have a ratchet to prevent that from happening. Right, that's going on again with some data sheets. This is how typically a data sheet would look for a ratchet and pawl system. Right, so you have catalog number. They'll give you the pitch, and again, the pitch is the distance between each tooth. Right, number of teeth, shapes, etc. Right, and you notice something here, they will actually give you, and do that calculation for you, they'll actually give you the allowable torque. So this is how much torque the ratchet and pawl system could withstand. So for example, we have one here with 8.24 Newton meter. If it is, and that is the expected load, right? So if it is, we were to exceed that, or we exceed that with the safety factor, for example, we go to 20 Newton meter, for example, then it means that the ratchet and pawl system could fail. Right, so this is why you would see that your lift now would have a certain load rating. And it doesn't necessarily mean that of lifting the motor, but it will also be that of the limiting factor of the ratchet and ball system. Now, as you would expect, these ratings here would be grossly over designed, because this is intended most of the time for safety. Right, you don't want to have the load being at 10 Newton meter in this case here and it fail. Right, we want some ridiculously high load to fail, and you could see how thick the material is, how these things are usually designed. Right, so we have different types. You have some types with hubs. Right, we have types without hubs, like in this case here. Right, so we have the dimensions also to help to go ahead and do the calculation that we just now saw. But again, the manufacturer usually give those load ratings. And so this is just an introduction to ratchet and pawls, and as a safety mechanism, especially being used for lifting devices. Right, the jack stand for a car, for example, is a ratchet and pawl system. That is allow motion on one way. In order to have motion in the opposite direction, we need to lift it. Right, and that's for information, that lifting force at disengage will be a factor of this equation here. Right, so we could actually put in, we could actually model with a force. Let's just say we want to know how much force we need to lift the disengage. So we want to put a motor or a servo to lift that. Well, then you could go ahead and actually calculate that from this equation. Right, you just include F into your calculation, into deriving the equation. Right, so that just concludes this very short introduction to ratchet and